Okay, so it's being recorded now, and so we can make this available to a wider audience. Before, we'll get to Daniel's presentation in a few minutes, but before I do that, it occurred to me that I had some slides from a talk that I gave a couple of years ago at AAS. They wanted me to give an overview talk on deep learning, and I think it would be worthwhile if I took 10 minutes and ran through a bit of that to give a big picture overview of the topic, to sort of set the stage for his presentation. So I think I'm going to start with that.
Chad, I think you only sent the slides to Daniel and me.
That might be the case.
I confirm I did not receive them.
So how can I send it to people easily right now?
If you have it on Dropbox, you could put a link in chat. If you have it on Space or...
Tom, it was you speaking, right? If you have them and you can share them on the...
Yeah, go ahead. Yeah, you start, Chad. I'll
yeah, sorry about that.
And if you can share them on Slack on the Science Collaboration channel, I can propagate the link from there.
Oh, okay, great. It'll take a minute.
Okay, so again, yeah, these are slides from a talk that I gave. I assume everybody can see them. The title was The Potential of Deep Learning with Astronomical Data. So I pulled out a few from this to hopefully give a bit of an intro to the topic. Sorry. So to me, a lot of this comes down to representing data. So we get data in a very complex forms these days. We're talking about images, spectra, light curves that are very irregular spacing to them. They're not in a form which is amenable to what in statistics and machine learning we would think of as the standard analysis tools. And to me, this is sort of the fundamental challenge of working with what's colloquially called big data, with this sort of complex data. Getting things into a form where they can be fed into a reasonable analysis. So, for instance, what summary statistic, if you're given a data collection, what summary statistic retains the important information for estimating cosmological parameters of interest? That question falls into this broad category. Or what features are most useful for classifying objects? This is obviously relevant to what we're discussing today. So going back to this, if I'm looking at classifying blazars versus CDs, and I get these complex time series, as we would call them, or light curves, how do I transform these objects into something that I could fit, that I could send into any sort of machine learning method, such as random forest or any of these classic methods people are accustomed to? That's a big question. And one thing that's done is to convert into structure functions, right? To look at differences in the magnitudes on the log scale at different time points. So this is a new representation of those light curves here. That's a way of transforming it into a space where hopefully you can do classification. So what have people done? They take these structure functions and they try to fit models to them. Maybe they assume a simple power law form or a damped random walk. But I don't want to focus on those specifics, but the big picture is they're trying to find a low-dimensional representation of these complex data objects so that they can then do classification. It's really an effort to avoid the curse of dimensionality, this sort of fundamental challenge of working with high-dimensional data, right? So here's an example from where they did this for quasar, with quasar light curves, fitting straight lines through these structure functions. Again, as a way to sort of take that high dimensional object and summarize it down into something that can then be fed into a classifier. So ideally, you could use a higher dimensional representation. You would not have to do this compression. You could work with the data in a more basic form, closer to its raw form. So that is where I think this entire discussion of deep learning really fits in and where it really can be useful. And if you read the paper or read some of it, that is a thing they focus on in explaining why they feel like this is a good approach for classification. So this is just a quote I took out of this, it's not a standard text in deep learning. You can find it online at this URL if you're curious, but there's a particular kind of machine learning that achieves great power and flexibility by representing the world as a nested hierarchy. So you start with these very complex data objects, and then through a sequence of layers, try to boil them down to their important features, and then do the classification. But there's a lot less user input in choosing those features. This is just a schematic showing how you go from the input to the output. So what do we mean when we say it's deep? The number of layers.
Question, is it better to hold till the end?
Yeah, go ahead if you have a question.
So, I mean, I've often heard that deep learning networks are better because they're dealing more with fundamental data, but as a result of doing all of these layers, you're actually doing an internal dimensional reduction. And so, in the sense that it's not somehow going from a high dimensional to a low dimensional space is not really true, is it? It's just that the user isn't determining what those features are ahead of time. Is that fair to say it that way?
Yeah, that's the user isn't forced to decide which features to choose. I think whether or not you're going from high dimension to low dimension sort of depends on how you set up the network. I mean, you can constrain it in such a way that you do sort of a compression. It's used for that purpose in some situations, but it's not necessarily going down to a lower dimensional space. If I said that, sorry, I misspoke. But you are sort of trying to avoid that problem of having to make low dimensional feature selection by yourself. So this really goes back to classic neural network models that have been around for quite a while. The sort of deep aspect of it is that the number of layers from top to bottom is typically quite large, allowing for the modeling of very complex relationships. Why has it become so popular lately? Obviously, this is a topic of great interest, but we have much larger training sets to utilize so that you can actually fit these very complex models. That's pretty important. There's better algorithms for training them. That, again, is a necessity. More computational resources, and it's proven to be successful in a wide range of situations. And again, Daniel in the paper, they cite some examples of that if you're interested, of areas where this has proven to be really successful. So there's a lot of flexibility, and this is either, I think, the great thing about it or what makes it very challenging. There's a lot of flexibility in how you can set up these models. You have to decide how many nodes, how many units there are in each of the layers of the model. You have to decide how you map from one layer to the next. And then you make a decision as to how you actually construct the output from the final layer, the final so-called hidden layer. So there's a lot of flexibility in how you can set up these models. Maybe a few too many knobs to turn. So I want to focus on this issue right here, the mapping from one layer to the next. Just to give an example, so the standard, maybe the basic idea is to use a so-called fully connected layer. where you're just taking linear combinations of the input from either the data or the output of the preceding layer. So I have a little diagram here, which took quite a while to put together, so I'm going to show it. I hope it's useful. So we imagine we start with this X, this input. Maybe that's the light curve or an image, whatever. That's the input into this neural network. So at this first layer, we're going to take particular linear combinations of the X. So maybe we can write it like this. So the input is d-dimensional. We're taking some linear combination of those X's, and then we add on some intercept, commonly referred to as the bias. So let's write that in vector notation. So that's one linear combination. But in this layer, I'm not going to just have one. I'm going to have several of these. I'm going to have M of them. M different linear combinations. So each of these weighting vectors is different for each of these M linear combinations. And then to each of those linear combinations, I'm going to apply a so-called activation function, which is just a very simple nonlinear function. Here are some examples right here. Very standard choices for this activation function, so-called rectified linear unit, where it's just a bend at 0. Or maybe it's these other smooth nonlinear functions. So the model proceeds by taking these transformed versions of these nonlinear functions and then going down through successive layers. So these first layers are mapped into the second layer. Again, the activation function is applied, and then on down the line. Any number of additional layers of this form, and then finally we reach the output. So again, and on some level, it's a very standard, it's kind of a simple model in some respects, just taking linear combinations and applying this nonlinear transformation. But the complexity comes from the size, the number of layers, the number of nodes in each layer. You can model very complex relationships using this if you allow it to be very deep. All right, so just how do we go from the actual output layer from that final hidden layer? Well, so for instance, if we had a continuous output, we might just use the linear combination of the final, some weighted linear combination of the final layer. So like a typical regression problem, we might use an output such as this. Or, sorry, that's the output of the final hidden layer. Or if it's a binary classification problem, there's the so-called logistic sigmoid function. So we're taking that final output layer and mapping it to something between 0 and 1. So what's the probability it's a Blazar versus a CB? If it's a binary classification problem, we can map into that probability using this sort of function. But, and this is relevant to the paper at hand, if we have a multinomial classification problem, there's a so-called softmax function. So this is going to take the vector, the final output of the final hidden layer, and map that into a vector of probabilities that sum up to 1. So what's the probability it's of each of these 12 different transient classes? So again, these are different choices that the modeler has to make depending on the problem at hand, how they want to set things up. All right, so that I just gave one example, this fully connected layer of going from one layer to the next. But there are all kinds of different ideas out there. There's a lot of alternative mappings from one layer to the next. And again, that's part of what Daniel is going to be talking about in a minute. The so-called use of recurrent neural networks. With image data, people often use so-called convolutional layers. So taking the pixelated image and running a convolution over it to map into the next successive layer on down the line. So just briefly, why does it work? From a statistician standpoint, I look at it and say, instead of thinking carefully about constructing a model, instead of thinking about all the aspects as to what the relationship is between the input and output, I'm going to just hit this thing with a really, I'm going to use a large collection of very simple components to try to build up a model. And that's really what's happening here. We're taking all of these very simple individual nodes and these simple nonlinear functions, and as a collection, they can do a good job at making a prediction of the final layer. That's, I think, a very heuristic sense, that's why it works. And there's theory behind this. You can look up the so-called universal approximation theorem. With enough units, a single hidden layer can approximate to arbitrary precision any nice function. There's some assumptions behind that theorem, obviously, but it works in a wide range of situations. Deeper networks, instead of using one single layer, deeper networks use a lot of layers, and what has been shown is that they use units more efficiently than having only a few layers. And they're also easier to fit, and they have been shown to generalize better to out-of-sample data. So again, there is theoretical justification for using these deep networks. Here's a nice quote. For deep models, the maximal number of linear regions grows exponentially fast with the number of parameters, while for shallow models, it only grows polynomially fast. So the complexity of the model that you're fitting grows a lot faster with the layers than with the number of layers than it does with the number of nodes in only a couple layers, for instance. That's what that quote is trying to say. All right. This just talks a little bit about how things are fit. I don't want to get too far off track here. I know that Daniel's going to talk a little bit about this. I know, obviously, overfitting is still a huge concern. The standard approach to avoiding overfitting, to do some sort of regularization, is to use what's called dropout. So units in the model are they're at random excluded from the model during training as a way to try to average over all the possible models within that space. Again, this is something that's discussed in the paper a little bit, and I hope maybe we can get Daniel to discuss a little bit about how that works in this case. It's really trying to reduce the influence of an individual unit, right? And that's kind of the key to avoiding overfitting. You don't want any one component of the model to really drive the predictions a great deal. All right, so just to wrap this up, my initial discussion, I think this is best suited to situations where you have some sort of high dimensional input. It allows you some way of getting around the curse of dimensionality, and it's definitely particularly relevant to classification challenges, which is what we're going to discuss next. Here's a few of the papers on the last slide. I hope Tom was able to get it out to everybody. But again, I think the big picture is you can start with high dimensional input, and with this very complex model made up of simple components, you can hopefully arrive at good predictions or classifications for the problem at hand. All right, so with that, maybe we should switch over to Daniel. I think it would be best if we have his presentation, make sure we have time for it, and then we can discuss more afterwards or later on as well. Does that make sense? Are you all set, Daniel? All right, great.
you want to stop sharing your screen so that I can try and share mine?
Oh, sorry. Yeah.
Thanks. Great, so I hope you can all see that.
Yeah.
Yep, so I'll talk about this software I've developed called Rapid and how we're using recurrent neural networks to classify light curves. So, we're currently at this pretty incredible time in astronomy where we have this unprecedented amount of data going to become available. Like surveys like the LSST here will really transform the transient universe, observing millions of alerts every single night. And so I think as such, new software, new tools that use machine learning are going to be necessary to be able to cope with and classify and process this amount of data. And so we've developed Rapid to do early classification of transients much faster than previous methods and in real time. So able to classify thousands of light curves within just a few seconds. So I'll get into how we actually do this. So firstly, well, we'll talk about why classification of transients is particularly important. So it's a good problem, particularly for LSST. I'll talk about the deep neural network architecture we've developed and how we've made this into an open source tool for the community and how we've applied this to both simulated and real data. And so this is where we'll end up at the end, where we're able to classify light curves as a function of time. So as the light curve evolves, our classification probabilities evolve as well. Okay, so we know transients are important. Things like supernova led to the discovery of the accelerating universe. Recently, the Nobel Prize was won for the kilonova discovery, where gravitational waves were detected by two neutron stars merging together. And so they're important, right? We all know that. But the more that we learn about the transient universe, the more that we learn how mysterious and how little we really know about it. So there are these areas that we kind of understand, like these thermonuclear, these type 1a supernovae, kind of these core collapse supernovae. There's a whole plethora of other objects and other areas which we have very little data of, and we don't really understand. Things like these calcium-rich transients, these superluminous supernovae, 0.1 explosions, even kilonova somewhere around here. And when LSST turns on, we're going to obtain an unprecedented number of these objects and hopefully get a lot more data points of these. And we need to be ready to be able to process these because we're not going to be able to look at every single light curve when millions of alerts are being processed every single night. And so a lot of the time we're going to need to follow up what we find, and we're going to need to be able to prioritize follow-up based on not only what type of object we think it is, but also on how early we think we've found it. So for example, in the case of type 1a supernovae, we don't really understand the progenitor systems. Is it a white dwarf accreting mass from a massive star and then reaching some change or seeker limit and exploding? Or is it two degenerate white dwarfs orbiting each other and reaching some explosion and exploding? So we don't understand progenitor systems. And one way we can actually understand that is by getting spectra early. So if we find a type 1a supernova, we know we've found it within a few days of explosion, we want to get a spectra and we want to prioritize that. But if we find a 1a that's very late, perhaps past maximum, then it's not so significant to find these because, maybe we have enough of those objects. So we need to be able to prioritize objects on when we think we've found it and what type of object we think we've found. So I'm sure you all know, but what is a transient and so how do we find them? So when LSST takes an image of the sky, so this is actually the best camera, but when LSST takes an image, what it's going to do is it's going to compare that image to some reference image, and eventually it'll get some change in brightness. And that change in brightness is a transient, and we call that a difference image. If we take several difference images over a function of time, we get a light curve. And so that's this evolving over time. And you can see that as the light curve evolves, the wavelengths of light that it's emitting evolve as well. And so we get a spectrum of light at each different point. And if we integrate under this particular filter, we'll get a light curve in a particular waveband. So that's what a light curve is. And so what's our problem? So we want to be able to classify a range of different types of light curves. But this is a problem, right? So if we want to build a training set to actually classify this amount to this kind of data for LSST, well, LSST isn't on yet. And so we can't really build a training set from real data. Now, what I've tried to do is, maybe we can build it for something that's currently on right now. This is called the Zwicky Transit Facility, which is a precursor to the LSST in just the R and G bands. And so can we try and classify that? Now, ZTF has been on for just over a year now. And, perhaps it's got enough type 1a supernova to inform a good training set. But it doesn't have enough of these rare types, things like these calcium-rich transients, these tidal disruption events, even kilonovae. It hasn't found enough of these objects to inform a good training set. And so the question then becomes, can we create a training set purely from simulated data and inform that and use that to classify real data. And so that's what we've tried to do here. And so there was this program called Plastic by LSST ISSC, which is called the Photometric LSST Astronomical Time Series Classification Challenge. And that produced this challenge out to the community to classify light curves. But more importantly, what it did was it created a simulation suite to create light curves that mimic the light curves that LSST will observe. So matching the observing properties, matching the cadences, and matching the number of filters, etc. And so what we did is we repurposed that software and applied it to this wiki transient facility. And that means we match the observing conditions, we match the pass bands, we create light curves like these. So these are examples. We've got things from a range of different types of supernova events, all the way down to superluminous supernovae, parent stability supernova events, intermediate luminosity transients, and all these other rare types. Okay, and so these are what we've simulated, and we simulated 48,000 of these light curves, split among these 12 different classes. So how have people tried to approach this problem before? Because people have tried classification before, and in general, no one's really tried. Very little attempts have been applied to early classification, and so that means that most people are looking at the full phase coverage. They wait for the entire light curve to be observed before a classification can be given, and that means you're not really making use of the time series or sequential information embedded in this. You're kind of treating this entire thing like an image, and not looking at the fact that neighboring points are associated with each other in a time series or sequential manner. On top of that, very little focus has been applied to early classification. It's just waiting until the entire light curve has been observed. Often approaches use something called feature extraction, which is very slow. And we heard a little bit about this, but often other techniques other than deep learning often require you to do feature extraction so you can reduce the dimensionality. And the problem with feature extraction is that it can often be very, very slow. So for example, what you might do is you might compute a periodogram of a light curve, and that might take a lot of computational power. And when you're getting millions of alerts per night, that is far too much computation power to be feasible, particularly for the likes of LSST. And so maybe that's fine if you just want to get a full catalog of light curves or type 1A supernova or a particular type at the end of a survey, at the end of LSST. But if you want to classify things in real time so that you can do real-time follow-up, you need to be able to classify things quickly. And so to do that, we'd much rather just input the raw data or some sort of lower computational process that representation of that data. Other than that, so other approaches have applied this, but they've usually just applied either binary classification between 1As and non-1As, because that's what most cosmologists are interested in. But we're very fortunate to have this large array of different types of light curves. So very recently, a similar type of work has been produced by Anais's group called Supernova, and they apply a very similar approach to ours. All right, so what is RAPID? So RAPID is this real-time classification software. We're trying to do classification as a function of time. So if we look at this light curve, this is an example of a type 1A supernova, and you can see that as the light curve evolves in time and as we get more and more data points, our classification probabilities change as well. So you can see this gray line is our pre-explosion. That's a class we've trained to learn what a pre-explosion is. And you can see that at the start, that's what's the highest probability event. But as the light curve evolves and we pass through the explosion point, which I've labeled as this dotted line, my model predicts that, and get closer to the maximum, you can see that the green line, the type 1A supernova, becomes more and more confident that that is the true classification. And by the end of the light curve, it is very, very confident that that is in fact the true classification. And so that's what we've done. We've applied, this is what RAPID does. It's able to do classification of real objects like this. And what we did is we simulated, we created this 48,000 light curves, and we split it into a 60% for training data and 40% for validating, for testing the data to evaluate the performance of our classifier. All right, so there's a lot. This is how we built RAPID. Okay, so there's a lot going on here, so I'm not going to go into all of it, but I'll try and break it down a little bit. So the inputs to RAPID are just multi-band photometric information. So in the case of ZTF, it's just R and G band. In the case of LSST, it'll be U, G, R, I, Z, Y. And we put in some contextual information. So if we have a host redshift or a photometric redshift, we'll pass that in as well. We'll pass in a Milky Way extinction as well as a vector above as well, above the light curve. We'll do some sort of pre-processing where we'll correct for Milky Way reddening. If we know the redshift, we correct for time dilation, and assuming some cosmology, we correct for a distance as well. The main part of our classifier, or the thing that really allows us to do this real-time classification, is the way that we label the light curve. And so you can see here, so this is an example of a type 1A supernovae, And what we do is, instead of labeling this entire object as a 1A, which most classifiers will do, what we do is we label this as a function of time. And so that means that every time step along this light curve gets a different label. And so what I've done is that I've created a model that predicts when explosion happens. And every time step before that explosion line, this dotted line, this dashed line here, I label as pre-explosion. So it learns what background noise looks like, or what a host looks like, what not a transient is, or pre-explosion looks like. And everything after this dotted line, I label as a particular type of transient. So in this case, it'll be a type 1A, and so I label that as a 1A. And so if we go back to here, this is the matrix that we're inputting. We have R band as a function of time. We have G band as a function of time. So every column is a time step. And we also put our redshifts and our time steps. But our actual labels, so this is our label matrix. We put a 1 for the green dots here are 1s, and everything else is 0s. So before T0, where my explosion happens, I label it as 1s. And after T0, I remove those pre-explosion points, and now this is labeled as a type 1A supernova. And if it was labeled as something else, I put 1s there instead. And so this is kind of a one-hot matrix representation of our labeled data. All right. Okay, so how do we actually classify? It's the actual classification stage. So we split this training set, we split the testing set. We create truth tables from these things, but the actual classifier. So what is the architecture of RAPID? And this is it over here. So I'll try and break this down a little bit, but you can see that at the top, we've got our input light curve. And so that is, each column is a different time step. And this could be our input matrix. That's this over here, different fluxes as a function of time. Okay. And so what we use is something called a recurrent neural network. And we use a variant of that called a GRU, a gated recurrent unit. And so before I get into exactly what these are, recurrent neural networks really came to fame with things like predictive text algorithms. So when you're typing on your iPhone and you are trying to predict the next word, that's a recurrent neural network operating right there. But most importantly, and where I actually got the idea for this kind of architecture, was from something called trigger word detection. So you've heard of like Apple Siri or Amazon Echo or Google's Home, those devices, where you say some word like "Hi Alexa," and it triggers the device. That there is called trigger word detection, and that employs recurrent neural networks. And what's really interesting is the shape of the data of someone saying "Hi Alexa" and recording that is actually very similar to the shape of the early part of a supernova light curve, right? So when someone says "Hi Alexa," you basically get nothing, nothing, nothing. Someone says "Hi Alexa," and you get this rise in magnitude in a range of different frequencies of sound. That's very, very similar to a supernova, where you've got nothing, 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 rise in magnitude of different wavelengths of light. And so we can employ a very, very similar architecture to what's being used in these big industries, which have invested a lot of effort into these kind of algorithms. And we can employ almost an identical architecture. Now, obviously, it's a little bit different. Our data is a lot more sparse. We can't just get observing time whenever we want, or like they can just place the recording device wherever. We have different noise properties, and we have a multi-class system. So rather than just being a binary event, did someone say "Hi Alexa?" We've got all these different classes to classify. But the architecture is very, very similar, and so we can employ that kind of software, which is a really exciting opportunity, I think. And so how does, so I'll go into these recurrent neural networks. Before I get into recurrent neural networks, now we heard a little bit from Chad about how these neural networks operate, but I'll just overview that a little bit here. And so this is an example of a feed-forward neural network, this fully connected network that Chad was talking about earlier. And what that is you can see you've got input. So for example, this could be your fluxes, and you've got some hidden layers, and you get your outputs. And your outputs might be the actual class, or what type of object it is. What's the probability of it being a 1A? What's the probability of it being a type 2 supernova? What's the probability of it being a TD, etc. Now, oftentimes we call this thing a black box. We call all these neural networks black box because we don't know, because it's such a high dimensional representation going on inside here that it's very difficult to interpret that and to figure out what's going on. What features inside here correspond to the features out at the light curve itself. And so we call that a black box. But calling it a black box doesn't mean that we don't understand the neural network. The mathematics behind a neural network are very, very well understood. In fact, it's extraordinarily simple. So you can see here that a neural network is just made up of a ton of linear equations. You've got something called a weight, and you've got something called a bias. So every line has an associated weight associated to it, and every node, this neuron, has an associated bias. And so we just sum all the lines connecting to a particular node, multiply that by a value. That's the weight times an x. And you get this value here, and you add the bias to it. And bam, you get your particular output layer here. And you repeat that process for every single neuron in your network over several layers. So the fact that it's deep here, we've got several layers here, and you can do that. And so that's it. It's just linear equations applied throughout your network. Now, oftentimes, we want to bring some nonlinearity into our network to be able to classify nonlinear parts of our input data. And so what we'll do is often take a function, an activation function of this linear equation. And so what is an activation function? An activation function it can be anything. It introduces nonlinearity into our network. It's good for stacking our layers, and it can keep our output values bounded between, say, for example, 0 and 1, rather than allowing it to extend to infinity, which allows the computation to be a little bit simpler and to be a little bit more bounded so that the gradient descent optimizer can be computed more efficiently. And so some examples of activation functions are these. So in convolutional neural networks, oftentimes you'll hear these ReLU functions, these rectified linear units being used. And what that does is it's nonlinear, right? You've got 0, it sets everything, all neurons that have a negative value to be 0, and all values positive to be that particular value. So it's just a max function here. In recurrent neural networks or fully connected networks, within the network itself, you'll often find either a sigmoid or a tanh function being used. And these are really great. So sigmoid functions, things like softmax regression, are really good for classifiers. It stores our value between 0 and 1, which is often very good. The tanh function is very, very similar. It's just a little bit steeper, so that you can have a steeper gradient than the sigmoid function. Maybe that's useful for your particular network. Which one to use is still an active part of research. Yeah. Okay. So that's what we apply here. And so feed-forward neural networks is what we've shown here. Okay, that's that. Now that means that we can only move in one direction. So our data is coming in one particular direction. It's only looking at a particular state of our network. So our input layer here could just be a particular time step going in and classifying a particular point. The information never touches a node twice. And feed-forward neural networks have no memory of any input they received previously, which means that they can't predict what's coming next. And so what we're using instead is something called a recurrent neural network. And so these feed-forward neural networks just take inputs from itself, but a recurrent neural network is able to not just take inputs from the previous layer, but is able to remember the state that it had at the previous time step and take that as an input as well. And we call that backpropagation through time. And so that it's able to update the weight parameters based on what the weight parameters were previously. And so it's able to remember this information in the sequence, and that's very, very useful for time series or sequential data, things like light curves. So this is a typical representation of a recurrent neural network. You can unroll this out, and that's this here, right? So inside here is the mechanics of the recurrent neural network, but our inputs are things like our fluxes at different time steps, and our outputs at the final layer will be our probabilities, but otherwise it's just the next layer in our network. And so it takes two inputs. It takes the current flux time step input, and it takes the output of the previous node. So it can retain a memory of previous time steps. All right, so this is the most simple recurrent neural network is here. Now, this might look complicated, but it's not, right? It's just a normal neural net. It's just you're applying a tanh function to a weight and a bias, right? You've got an input here, and you've got that linear equation, which is this function here, and you've got your input from the previous point here as well. And so you just do another linear equation. You put a tanh function around either of those. And so that's a recurrent neural network. Now, the problem with the recurrent neural networks is that these are great. Recurrent neural networks are fantastic, but they really weren't popular for a long time. They were developed in the 80s, but they weren't very popular. And the reason was they didn't really deal with sequential information well. And the reason for that is it can only really store information at very recent times. You can remember just the previous node. And as the time steps increase, it loses complexity to derive context from the previous time steps that are too far behind. And so to combat this, something called long short-term memory networks were developed in 1997. And this really came a long way to solving the problem. So a normal recurrent neural network just has a tanh function. It's got your input flux, you've got the state of the previous network as an input. Now, an LSTM, these long short-term memory networks, has a lot more complicated things going on here. Now, I'm not going to go into each of these here because I think it's out of the scope, but what this complexity allows you to do is allows you to remember more about previous time steps and store store memory of not only the previous time step, but all the previous representation of the network before that as well. And so that's an LSTM. Now, a GRU was developed in 2012. It's very, very similar to an LSTM. It's just a slightly a condensed version of it. And so that's what we use here. It allows for a little bit faster training time without losing too much of the performance. So that's what we've got here. So these are the GRUs. We're taking inputs at different time steps, and each input takes the input of the flux at a particular time step, but also the input from the previous time step. We've also got a range of other things going on here. So we've got 2 layers of GRUs. We've got dropout layers, and we've got batch to reduce overfitting. We've got this batch normalization to speed up training. And we've finally got this fully connected layer, a dense layer, and a softmax regression at the end. And so I'll go into, so firstly, dropout. What is dropout? As we heard briefly from Chad what dropout was. And so often neural networks can overfit data because it's got such a high dimensional space, you can nearly fit anything. And if you want to generalize well from training data to testing data, you don't want to overfit your data too much. And so dropout is a way to combat overfitting. It forces a neural network to learn more robust features such that no individual neuron is relied on too much. And so, for example, so what that basically does is, a fully connected network like this is here. What dropout will do is it will randomly remove the connections to particular neurons throughout your network. So you might set some rate, maybe set it to 20%, maybe set to 80% of neurons, some rate, and those neurons are removed from activation for that particular run of our training set, of our iteration of the training set. Now, every training set will randomly select a new set of neurons. Every time it runs through a data or a training set, it'll set a new set of neurons to rely upon, and so that means that it'll never become too reliant on a particular neuron. And so that means that no one feature in our light curve is going to be particularly important or too significant. And so this allows us to reduce overfitting a little bit with this regularization technique. Now, it does increase the computation time or the convergence to actually calculating it, to actually classifying it, to actually training a classifier, but it's often worth it in the long run. And so, so the way this works is that each neuron is present with some probability p, and we can set that rate p. Okay. And so that's that, right? That's the dropout neurons. So the batch normalization, now what that does is it basically forces our weights and biases to be normalized among the entire vector, and that allows just for faster training. I won't go into actually the mathematics behind it. There's a nice paper on it, but it's a little bit complicated. Now, the final layer is to get our output probabilities is a dense layer, a fully connected layer, and then a softmax regression, so a softmax activation function applied to that dense layer. And so what a softmax activation function looks like is this. And so it takes the outputs of a network and applies the softmax regression. What softmax regression is, it basically normalizes all our values between 0 and 1 such that our outputs are basically like probabilities, right? We've got a value stored between 0 and 1. Now, that's how we were able to get this classifier, right? And we can produce this. We have our input fluxes in the top here, and our output probabilities plotted here. So each of these y's is a vector, and that's a vector at different time steps that we are plotting here. Each vector containing the different probabilities of each of our 12 classes. All right, and so what we can actually do is we can create this kind of light curve with this kind of classification probability vectors for every single light curve in our testing set. And then what that allows, sorry.
Quick question. Did you try different architectures? Was there a particular reason why you used this one? Why 2 GRU layers?
Yeah, so I mean, so the initial reason I chose this architecture was it worked really well for trigger word detection. But I did play around with adding a 3rd GRU. Let's see what happens. But this is all, it's very hard to do this in a systematic way because the training time is so long. But I did just play around with it and see, did the classification performance improve when I added a 3rd GRU? Not really, so I left it out. Did it reduce in any way when I removed one of the layers? Yeah, it did a little bit, so I left it in. And so it was kind of like, I mean, that's the issue with neural network with deep learning at the moment. It's a little bit of playing around because the training time is so long. You struggle to change your architecture. What you can do, and what I did do, is you can change the parameters that you apply to this architecture. For example, I selected 100 neurons in this particular GRU, and I selected a 20% dropout activation function, but I varied those. So I tried about 12 different hyperparameters for each of these things, 12 different combinations, and that allowed me to optimize, well, not optimize, but at least try out a range of different hyperparameters and select the hyperparameters that best classified at the testing set for this particular architecture. And so we can create these kind of these classification probabilities for all of our testing set, and what that allows us to do is it allows us to create metrics as a function of time. And so that's what we can plot here. We can plot a confusion matrix, which is basically plotting how many of true type 1a supernova, for example, were correctly predicted as type 1a supernova. And so ideally, we want this to be diagonal, where all of the diagonal elements are 1 and all the off-diagonal points are 0, meaning that we've got no misclassifications and everything's classified perfectly. But you can see that as the classification, as the light curve evolves in time for each of our light curves, the probability increases as well. So you can see towards the end of this light curve, we get 92% of type 1a supernova correctly predicted as type 1a supernova. On the right here, we've got another metric we can use, something called a ROC curve, which is a receiver operating characteristic curve, which plots the true positive rate against the false positive rate. And ideally, we want the area under this curve to be 1. We want to maximize the area. So you can see that everything moving towards the left here and to the top left is really good. It means that we're maximizing the area under this curve. And so that's these things I plotted in the brackets here is the area under the curve. You can see we do quite well for some of the classes, but we do some not so well in some of the other classes. But in general, classifiers that achieve area under the curve performances above 90% are particularly good.
Daniel, I have a question, if you don't mind me interrupting. So when you say as a function of time, you are actually, I mean, there's two possible, meanings of time here. One is, of course, the training of the network, and then the other one is just the steps of the light curve. So you are inputting the light curve with different number of time steps, and then for each of them you're training and then outputting only the probability after training when you do this exercise.
So when I say time steps, I'm talking about the time step of our light curve, and so that's I take 3 day, I interpolate this and I take 3 day bins. And so I guess
I refer to the probabilities that you're putting in the lower plot to the right here. So those are for different numbers of points of the light curve, you run the train network on those limited numbers of points, right?
Yeah. So I didn't actually. So the nice thing about using a unidirectional recurrent neural network is that I don't actually have to create a training set with light curves cut off at different time steps. I don't need to do that. I can put in a full light curve and just extract the probabilities at each time step, because no particular time step is using information from a future step.
Right.
And so I can just take out the probabilities here and plot that, take out the probabilities here and plot that at a particular time step, take out the probabilities of this vector and plot that at a different time step. And that's for any shape of light curve. So I can just use any light curve without having to augment my training set by different time, by cutting it short or anything like that.
Okay, yes, I think that's what I was asking. Thanks.
And just to follow up on that, so the Y0, Y1, etc. need to mean the same thing for every light curve. So did you say you interpolated the light curve somehow, or?
That's right. So I interpolated this light curve, and I interpolated to include 50 points. So n here is 50, so it's 50 points here between minus 80 days and minus 70 days and 80 days after something called trigger, which is the 5 sigma signal to noise point of ZTF.
I see. And how was the interpolation done?
There's a linear interpolation. And so, and so that works quite well to do this. We've tried this in LSST, which has a lower cadence. It performs reasonably, but time will tell whether or not interpolation is a good point. Because there are other work, for example, Anaïs's work doesn't do interpolation. Instead, they just input fluxes. They just input fluxes as one vector and delta t's, the time difference between points, as another vector. But yeah, we've gone with interpolation so that we can do different times. So each time step here is 3 days apart.
Thanks.
Great.
One quick question. How do you handle gaps in the data?
So I still interpolate between those points, and that's what goes in.
Okay.
So this gap here, for example, is still going to be whatever in linear interpolation occurs between these points. Because obviously we don't, like ZTF's cadence is supposed to be 3 days, but it's not always 3 days. So this can lead to issues. But as you know, as long as the way, I mean, hopefully if our training set covers a lot of this, it'll covers these different types of, with our training set has gaps in it, as just like the real data has as well, then it might be able to recover some of that. It learns that, the particular value, is at a particular point is, well, I mean, it learns that, gaps do exist and some points shouldn't be taken so seriously as others. But
So how do you treat the errors, the photometric errors then?
So right now, errors don't go into this classifier. And so that's something is room for improvement. I'd really like to come up with a good way to introduce errors into this. But right now, no, the errors don't actually come in.
And so it's just a piecewise linear interpolation from the previously measured point. Is that correct?
Yep, that's right. It's just a linear interpolation to each point. If we didn't want to do a spline or anything like that, because we don't want to assume anything about the future part of a light curve.
I have another question on that. Sorry, Dan. Have you tried, instead of doing interpolation, just putting a default value for missing data, or not at all? Yeah, so I haven't tried it in depth. So recently, I've had a go. This is kind of a similar approach to what your work was, where you just put in the fluxes and delta t's as your inputs. I haven't explored that well enough, so I don't know how differently it performs. Cool, thanks.
I have a question as well.
Mm-hmm.
Two really. One is, you are giving the apparent magnitude of the object, right? So inherently, you are giving photometric errors. I mean, at least at the level of like, what is the brightness luminosity?
Yeah. So I mean,
LSST will have very low systematic sensitivity. And then the other question is, have you tried with very fast transients? Does this bias you against discovering very fast transients? The fact that you interpolate. So, I mean, we've got things like kilonova, which are quite fast. I think that's the fastest event in our list. And it's able to classify a lot of those. Now, one of the problems there is that, I mean, if a point doesn't exist at the maximum, so I think at the cadence of ZTF, often you'll only get about 1 point before, or 1 or 2 points before it drops down. And so anything that drops down and falls very quickly will often be classified as a kilonova by our classifier, because it knows that's very fast. But if you're missing those points, then it's not really going to see that. It's going to probably predict that as a pre-explosion the entire time. Yep. Thank you.
Okay. Okay, so we can see that our classifiers improve over time, but you can see that it doesn't do too well, for example, at these core collapse supernova events. You can see that these are quite misclassified, often as calcium-rich transient, these 1BCs. And so while it's difficult to actually open up our black box and look at why these 1BCs are being classified as CARTs, like which particular parts of the input are actually causing this, we can plot the correctly classified and incorrectly classified ones, and we can see they all look quite similar, so we can kind of forgive our network for making these kinds of mistakes. But perhaps in future, more color information will improve that. So over here, I've just plotted the area under the curve from our ROC curve as a function of time as well. Okay. And so this is all applied to simulated data. And then the question is, can we apply this to real data? And so we did. So the first time I tried this was not too long ago, where the first object I tried was one of my colleagues, James Gillishon, posted on Twitter. It's quite an interesting story that he found this object in ZTF. And it was labeled as a galaxy. And he's like, I don't think that's a galaxy. I'm pretty sure that's a TDE. And he fit his software called MOSFET to it. And he's like, it's TDE. Then I tried RAPID for the first time, trained purely on simulated data, and was able to predict a TDE as the most popular class within just about 4 or 5 epochs of the event. And so that was really, really exciting. We can go from simulated data and actually classify real events. And so we fit here. You can, and one of the nice things here is actually you can kind of do automated classification through RAPID, but also automatic characterization through something like MOSFET, where you can fit these light curves with what you think it is. If you think it's a TD, fit it with MOSFET, you can get out black hole characteristics, masses, velocity, etc. Then we applied this, so we've recently been applied this to real data in the ZTF data stream through Antares, and we've been able to classify a lot of real objects already. Now, it's still a work in progress. You can see that, here the type 1a supernova, very sparse data, doesn't look too great. It's still able to pick out a 1a as the most popular class, and within just a few days of the explosion time. And I think that's really, really exciting. Now, this is still a work in progress. There are some objects where it gets this wrong, and you really need to just make sure your training set, your testing set, your simulated set really does match the real data. And so we're iterating back and forth between that. But I've made this software open source. It's currently available on Python or on pip, or Python packaging index, pip install AstroRapid. It's well documented on Read the Docs. But we're currently applying this through Antares and LSST, these LSST brokers, which will be able to process the nightly streams of LSST and produce that out to the community. And so one of the output streams will be rapid classification, so that you can get what Rapid at least thinks the classification class of a particular transient was. And we're already classifying these in real time right now. We've got some, hopefully soon we'll be able to follow up these objects, some of the objects we find, and actually classify them with spectra in real time, and actually hopefully be able to find some interesting objects. One of the other problems in LSST is actually picking out a cadence model. And so one thing we can do is, people have simulated a ton of different cadence models already in LSST. And so what we can do is we can run these cadence models through our simulation software, this plastic simulation software, and simulate a range of different light curves at different cadences. And we can see how rapid performs on these different cadences. And what that allows us to do is it allows us to optimize the observing strategy or cadence properties for transient classification. And transient classification, so what type of, what cadence property, what observing properties will lead to really good classifications of TDEs, or what observing properties will lead to really good classification of 1As at very early times? What kind of cadence, what kind of days do you need? And hopefully, this is some work we're doing at the moment, and we'll be able to answer this question in at least some fashion. All right, so in conclusion, Rapid allows us to do this prioritized follow-up of these new large-scale surveys, things like ZTF, and hopefully eventually with LSST. It allows us to do early classification because of these recurrent neural network architecture. It can classify 12 different transient classes within just a few days of its explosion, despite not having that much color information and having quite low signal to noise. And it's very, very fast. It can classify tens of thousands of events within just a few seconds. And so it's well suited to the likes of LSST and right now ZTF. Thanks.
All right. Thanks a lot, Daniel. That was great. I think we can take a few more minutes if there are additional questions. I'm sorry we went a little over time, but...
Is this published already?
Yeah, so this paper is out on the archive and is accepted into PASP at the moment.
Mm-hmm.
I have a question if nobody else.
Go for it.
What is your sensitivity to the information, the astrophysical information that you add? You said you mentioned that you add redshift distance, things like that. What is your sensitivity to whether you had them or not, and to their accuracy?
So
I'm thinking of redshift and photometric redshift.
Yeah. So so we built two classifiers: one that has our redshift information input into it, and one that doesn't. Obviously, the one that has redshift is able to classify a lot better. And I mean, yeah, the one that doesn't include redshift is okay, but if we include a photometric redshift, I found that it works a lot better, even if it isn't a host redshift.
Thank you.
All right, if I can just kind of bring it back to a big picture issue of one thing that I hear people comment about deep learning is that they don't learn about what actual features of the data are useful for classification in a classification problem. Do you see that as being, have you gotten any comments of that sort? Do you see that being an issue here? Like from a scientific standpoint, we're not learning as to what aspects of the light curves are useful for separating different types out. Do you think there's any way of addressing that sort of question?
Yeah, so I mean, that's still a very open problem in deep learning. No one really knows how to open up this black box. If you've got a single layer, just a single hidden layer, you can actually do it quite well. So you've seen this applied to the handwritten digit problem, where you're able to take And so there's a really cool application online, which is quite nice, where you're able to actually look at which neurons in your next layer are highlighted by every segment in your network. But once you extend this to multiple layers, the abstractness and the abstractness of your network becomes way too complicated, and it's very, very difficult to actually to compare these neuron values to how that corresponds to these input values because of the high dimensionality space you've got here. And so that is a problem, and it's, is it unscientific to apply these things? Maybe, but we do know that it does work. And it does work a lot. And so, I mean, the best thing you can really do is to try and probe your network, try and put in different inputs and see how it performs differently. And so I think that'll be really exciting when we try this cadence optimization, where we'll be able to see how different cadence properties, observing properties, actually change our light curve classifications. And so not only will we be able to probe optimized classification performance, but maybe we'll actually be able to probe our network as well, to see how sensitive is it to cadence, how sensitive is it to color information per night or R-band information per night. And so right now, that's the best strategy we have, just probing your network by passing different types of inputs in it and seeing how it performs. But it's still, when you've got more than one layer, one hidden layer, it's still very, very difficult to actually look at what is, how do the input parameters correspond to your input data. I mean, it is a little bit unscientific in that you can't really control it right now. It's an open problem. Maybe one day someone will solve that. But we do know that these work very, very well. And it is, I mean, in the age of these big data things, I think it's worth trying. It's more that, you almost need to try it because there's no other good way to classify this amount of data in such an effective fashion.
Right. I completely agree. I think that very important methods to try. Go ahead.
I had a comment and another question. So the comment is about the previous question. I mean, the way I see this is the network is actually learning features, but you're not telling it what features to learn. Basically, it's learning a representation of the space that it's kind of, you can see whatever comes out before the output layer as the best features that represent the data to be able to classify it into the different types. That's at least how I see it. And the question was, so what would be the use of this? So did I understand correctly that you interpolate so that you have the same number of points for the light curves? So these are kind of these are all sampled at the same times. And would you see an use of this method in sparse light curves that are not necessarily taken at the same times?
Yeah, so I mean, one of the things with neural networks is often you need to have a fixed length input vector. And so that means that, so the way we come out of that was by doing this interpolation where we forced each network to have 50 points. If it didn't have that much data, so obviously most light curves don't have data between minus 80 days and 70 days. And so we zero pad everything else outside of the range of information it does have. And so that's the most common way to deal with that problem. Now, when you've got sparse data, maybe interpolation doesn't work well. We found that it actually is okay with things like the likes of LSST, and it's not so bad. But I mean, there are these other approaches, like I mentioned before, whereas instead of interpolating, you can, you just pass in a vector of your fluxes. Now, it doesn't understand which fluxes correspond to what time step, but if you pass in another vector above that with delta t, so the time difference between a particular time step and the previous one, that's actually an effective way to approach a sparse data problem. Yeah.
Thanks.
All right.
What is the training time?
I mean,
so how long does it take to train the network?
So this network here with the 2 layers of GRUs and training over 48,000 light curves, I run it over about 30 cores or so, and it takes about 5 hours or so. So neural networks, actually, one of the other problems with neural networks is they're actually a lot slower to train than things like random forests and other classifiers.
Wait,
another quick question. Another quick thing. You used the GRU cell, but actually I read that, for example, the GRU cell and the LSTM cell, they not performs very well on irregular on irregular data. There is a new cell that I think was published in 2016. It is called PLSTM, and it should be better for irregular data. So maybe it's something that is worth to try.
Yeah, so I've read about that recently. So there's a paper recently by Adam
Moss. Yes, Adam Moss.
They use these phased LSTM, these PLSTM, which is supposed to be able to deal with this irregular time sampled information better. I haven't explored that yet, but it would be interesting to try.
Yeah.
Okay, I think there was one last question. Was there somebody?
Yes, sorry.
Yeah,
My question was, I heard it was 5 hours for the training. Can you tell me if you use a GPU and how big was your data set? Because that seems rather a lot.
I didn't use a GPU, so that's probably why.
Okay.
I wasn't too concerned about, I didn't, at the time, I didn't have access to a GPU cluster, but yeah.
Okay, yeah, it should take much less with a GPU.
I'm sure it would, yeah.
Okay, great. Thank you so much, Daniel, for the presentation. I thought it was really useful. Again, if people have ideas for other topics, other papers they've seen, please shoot me an email and I will try to set something up. I'm hoping maybe by the fall semester here, we can maybe have a regular once a month schedule of these sorts of presentations. All right. Thanks a lot, everybody, for coming.
Thank you. Bye-bye.
Thank you.
Thank you.
Thanks to both of you. Great.
Bye.